So this video is working out the chemical formula of anything except the organic molecules, which have their own little rules, not that they're complicated. We'll face that on another video. So we're writing chemical formulae. This is part of a whole topic called stoichiometry, and really that's the relationship between the amounts of substances taking part in a reaction or making a compound. And it's clearly stated we need to state the formula of the elements and compounds in the syllabus. Now that's a lot. I can remember when I was at your stage, my teacher coming in and giving me a list of 50 formulae to learn. And I remember thinking, that's not going to happen. We have to have rules for being able to work these out. For example, sodium sulfate halfway down my page here. Na2SO4. I don't want to remember that, but I do need to be able to figure it. Magnesium hydroxide, MgOH2. Oh, but not for a memorization job. Yeah, we're looking at a lot of formulae. We need to simplify the task. Firstly, positive and negative charges have to balance in the formula of any ionic compound. Now this one, we could get given the formulae of ions that are present. And we always do that by balancing charges. The ion with a positive charge is always named first. That's worth stating. Always the cation before the anion. Always positive charge named before negative. Sodium sulfate. If I'm told sodium is Na plus and sulfate is SO42 minus, I realize I need 2 of the Na plus to balance the SO42 minus. Na2SO4. I use subscript. Magnesium hydroxide. If I'm told Mg is 2 plus and OH minus is 1 minus, or rather OH minus is that single minus, I need 2 of the OH minuses to balance the Mg2 plus, MgOH2. Now at this stage, let me make a mistake. I'm going to take this out. Very possible that someone could say, whoa, Mg for the magnesium, yeah. OH, I've got 2 of them and just write a 2 there. But if I do that, anybody might come along and might think MgOH, or rather O1H2. That's what it looks like. We have to put our brackets, our parenthesis in there to show that the OH as a group is there twice. Aluminium nitrate again. If I'm told aluminium is Al3 plus and nitrate is NO3 minus, I can see I need 3 of the NO3 minuses to balance the charge on the Al3 plus. Al parenthesis or brackets NO3 3 times. Aluminium sulfate, okay. Al is 3 plus, sulfate is SO42 minus. Oh, charge has to balance. The only way I can do that is to have 2 of the aluminiums, 3 of the SO42 minuses. Al2, SO4 3 times. It's worth noting you have to have that use of parentheses, that use of brackets, if there's more than one atom in a group. Couple to try. I'm given the charges. What's the formula? So for the first, I've got magnesium, Mg2 plus. I've got sulfate, SO42 minus, balancing the charge, MgSO4. For the second, NH4 plus, I see that's a group already. SO42 minus. I need to have 2 of these NH4s as a group to balance the SO42 minus. The SO42 minus. Third, K plus, CO3 2 minus. I need 2 of those positive ions. K2, CO3. NH4 plus, PO4 3 minus. I need 3 of that positive NH4 plus to balance the PO4 3 minus. Now, what looked like a little bit scary to begin with really was not. Now, in working out the formula of any ionic compound, 3 steps. When I started to put this presentation together, I ended up with so many slides. I've divided it down to make 2 sets. In the first video, that's this one, I'm going to take 2 of these 3 steps. Step 1. This is when we only just get 2 elements combining to make a compound. And we know the group that they belong to. There's the periodic table, always there for us to use. We can use this idea of valency. It's not always taught in schools, but it just tells us the number of electrons that something needs to gain or lose. Elements in group 8 never react. They have a full outer shell of electrons, and that makes them stable. No need to react. Atoms of all other elements lose or gain electrons to get full outer shells when they react. And my number of electrons gained or lost depends how many there were in the outside shell to begin with. Elements in group 2 have 2 in the outside shell, they've got to be lost. Element in group 7, 7 in the outside shell, gain 1 to get 8 rather than lose 7. Now, sodium, for example, Na. I can see it number 11 in the periodic table. Number 11 tells me the proton number is 11, the electron number is 11 also. Electronic configuration must be 2, 8, 1. And we saw in a previous video that you could do that by like reading a book. Look at the top row, 2 elements. Look at the second row, 8 elements. Na is the first in the third row, the third period. 2, 8, 1. But my sodium atoms all lose 1 electron. Oxygen, looking across to the right-hand side, oxygen atoms contain 6 outer electrons. I can just do that from the group number. Li lithium begins group 1, Be beryllium begins group 2, across to oxygen, oxygen begins group 6. 6 in the outside shell needs to gain 2 electrons. 2 sodium atoms are required for every oxygen. Each sodium atom will lose 1 electron, the oxygen atom will gain 2, Na2O. Another example, magnesium sulfide contains magnesium and sulfur only. Magnesium is in group 2, so its atoms all lose 2 electrons. Sulfur is in group 6, so its atoms all gain 2 electrons to get a full shell of 8. Only 1 magnesium atom is required for every sulfur, giving me the formula MgS. And just to say, magnesium sulfide, the names of the elements used in the formula are given. That magnesium sulfide tells me it contains magnesium, yep, sulfur, yep, and the IDE is a little code, nothing else. Period, full stop, that's it. So my formula will be MgS, 1 magnesium atom providing 2 electrons, 1 sulfur atom gaining both. Another, carbon dioxide. Carbon and oxygen only. Carbon in group 4. Group 4 means 4 in the outside shell. 4 more electrons need to be gained. Oxygen in group 6. 6 in the outside shell already. 2 need to be gained. And when both atoms need to gain electrons, they share. That's covalent bonding. An oxygen atom shares 2 electrons with a carbon atom. So I need 2 of them. And that's shown with the representation of the lines between the atoms. Oxygen on the left, 2 lines, makes 2 covalent bonds with the carbon in the center. Same for the oxygen on the right. 2 bonds are made with the carbon in the center. I'm involving 1 carbon and 2 oxygens, CO2. Why CO2? Why not O2C? Carbons in group 4, oxygens in group 6. Lowest group listed first. Now I've got a number here to try. Aluminium chloride, and the group numbers are given below. I haven't given the group numbers for the lower line, calcium chloride, because they are that's using the elements that are already indicated in examples above. If I look at aluminium chloride, aluminium in group 3, chlorine in group 7. Aluminium atoms will lose 3 electrons, chlorine will gain 1. I need 3 of the chlorines. And if I put that here, AlCl3. Potassium oxide. Potassium group 1, 1 electron to lose. Oxygen group 6, 2 to be gained. I need 2 potassiums to combine with the oxygen, K2O. Calcium oxide in my second row. Calcium group 2, going to lose 2 electrons. Oxygen in group 6, going to gain 2 electrons. 1 calcium can do business completely with 1 oxygen, CaO. Now nitrogen chloride. With nitrogen and chlorine, I have got nitrogen in group 5 needs to gain 3 electrons, needs to make 3 bonds. Chlorine in group 7, 1 electron needs to be gained. Each chlorine needs to make 1 bond. Now, one thing I've noticed here, nitrogen chloride, there are 2 nonmetals. So I'm thinking covalent, NCl3. Calcium chloride, above we saw in our third example, calcium in group 2, it's going to lose 2 electrons. Chloride from chlorine, group 7, each chlorine will gain 1. 1 calcium atom will provide both electrons for 2 chlorides to combine, CaCl2. And everyone's favorite, aluminium oxide. Aluminium group 3 makes Al3+. Oxygen group 6 makes O2 minus. Balance the charges. Al3+, O2 minus. I need 2 of my aluminiums to give me 6 plus overall. I need 3 of my oxygens to give me 6 minus overall. That balances. We're done. So that's the way to do it. If I get 2 elements combined together to form one simple compound, I just look at the group numbers. Moving on. 3 steps. This is step 2. I'm only dealing with 2 steps in this video. Step 2 is actually easier than step 1. Again, when I just get 2 elements combining, but one of them is a transition element. Now, what does that mean? That means I can't use groups. Could be a transition element, or very, very rarely, an element showing an unusual valency. And yeah, in this case, it's actually easier. The valency is given in Roman numerals after the name. I'm looking at the first, copper 2 chloride. If I look at a part of the periodic table that's here, copper is Cu, transition element. Li, Na, and K are group 1. Be, Mg, and Ca are group 2. I would have group 3, 4, 5, the other side of the transition elements, but no need for them right now. So I'm looking here at copper. I can't figure out the charge. I can't figure out how many electrons copper atoms will lose. That's why we don't say copper chloride, we say copper 2 chloride. That tells me I'm dealing with Cu2+. Chlorine, to make the chloride, I can use the periodic table. Chlorine in group 7 is going to gain 1 electron. The atoms will gain 1 electron to become Cl-. I need 1 of my Cu2+ to combine with 2 single negative Cl minuses. And that gives me my chemical formula, CuCl2. In iron 3 chloride, iron is Fe, chloride again, Cl. I know because of the Roman numerals 3. I know that the charge on the iron is 3 plus. Chlorine is Cl minus. It's in chlorine is a group 7 element. 1 electron needs to be gained to get a full outer shell. That's Cl minus. Now, if Fe is 3 plus, I will need 3 of the Cl minuses to combine with it. FeCl3. There's my periodic table. That was being used already. A few more to try. Vanadium 4 oxide. Vanadium is V. Oxygen in group 6 forms O2 minus. I'll pause for a second. If it's vanadium with charge 4, that's 4 plus. I need 2 of the O2 minuses to balance the charge. VO2. Chromium 3 chloride. Chromium is Cr. So it's Cr plus 3. Chloride is -1. I've got my CrCl3. Iron, Fe. Iron 2 chloride. Fe must have charge +2, means I need 2 of the Cl minuses to bond with it. FeCl2. And titanium. Ti for titanium. Titanium 2 oxide. So titanium is Ti 2 plus. Oxygen being in group 6 forms the oxide O2 minus. 1 titanium to bond with 1 oxygen. Now we've seen IDE means full stop. Nothing else is there. The 4 I've got above me, vanadium oxide, contains vanadium and oxygen, full stop, period. That's it. Chromium 3 chloride, chromium and chloride ion. That's it. Iron 2 chloride contains iron oxidation state 2 plus the chloride ion. Nothing else. The IDE tells me that. Titanium 2 oxide, titanium, oxygen, and nothing else. That IDE is a giveaway. Now there could be a compound ending in 8, not ide. ATE is like a code. ATE means, watch out, oxygen is there also. And ATE really tells me that I've got a group of atoms holding together. This is what I'll deal with in part 2. But for now, sodium sulfate, I see the sodium named. Yep, contains sodium. Sulf, that's sulfur. And 8, that's always oxygen. They're present, so the sodium and the sulfur and the oxygen are present as a sulfate group. Now this group of atoms will either come from an acid, water, or ammonia. Hydrogen will be lost or gained when the group is formed. But that's part 2. For now, calcium sulfate, the ATE rule, contains calcium, sulfur, and oxygen. Iron 2 nitrate. Iron is Fe. Iron contains iron, nitrogen, and oxygen. Never mind the numbers. That's for part 2. Even good old water, ATE right in the middle, H2O. And in bio, one of the things we have to look at in biological molecules, name the elements present in a carbohydrate. Done. Carbo, carbon. Hydra, hydrogen. 8 tells me oxygen. Just so happens that the formula of our simplest carbohydrate, glucose, is C6H12O6. All we're saying right now is we're identifying the elements that are present. That's part 1 complete. Part 2 coming.